welcome students. This is the 7th lecture for this broad topic, that is open channel flow, and as we were going to start this gradually varied flow as promised in the last lecture. Until now we have studied that in open channel flow with the classification based on space, the dimensions. There are three type of flows. One is uniform flow and other is non-uniform flow. So, non-uniform have two different categories. The first is gradually varied flow and the second is rapidly varied flow. So, the next 4 lectures would be dedicated on these two topics, gradually varied flow and rapidly varied flow in the open channel flows. Okay, so, to get started we should understand what exactly a gradually varied flow is. We have already derived an equation before, but to make it more clear we will see it in a little different way, a derivation of a different sort. So, what is gradually varied flow? The flow in a channel is termed as gradually varied if the flow depth changes gradually over a large length of the channel. We said that dy by dx is very much less than 1, all right. So, this is the definition. So, I will just erase this. So, what are the assumptions behind gradually varied flow? First, that the channel is prismatic. This is the first assumption. This means, what does it mean by the channel is prismatic? That the cross sectional shape, size and the bed slope are constant. So, this is what it means being prismatic, all right. Second assumption is that the flow in the channel is steady and non-uniform. Non-uniform means that dy by dx, steady means dy by dt is 0, but dy by dx is not equal to 0. So, these are the some assumptions when we deal with the gradually varied flow. The third one is the channel bed slope is small. So, theta or S naught is small, S naught as we have been seeing in the open channel flow. The another approximation assumption is that the pressure distribution at any section is hydrostatic. This is an important one. Apart from that, the resistance to the flow at any depth is given by the corresponding uniform flow equation. This is another assumption when we are going to derive the different parameters and the properties of gradually varied flow. So, this is another assumption that the resistance to flow at any depth is given by the corresponding uniform flow equations. For example, uniform flow equations like the Manning's equation, for example, or Chezy equation. So, example is Manning's equation, all right. You have to remember that in uniform flow equations, energy slope SF is used in place of bed slope S naught. When Manning's formula is used, we get SF is equal to n square V by r to the power 4 by 3, okay, all right. So, this we have to keep into account. So, instead of the bed slope S naught, the energy slope SF is used. Now, what the going to the differential equation of the gradually varied flow. So, first we have to draw figure. I have shown you a figure here where there is a small bed slope, there is a channel with a small bed slope S naught. So, basically this theta is the angle, all right. The datum is given by this, this is the datum, all right, and the height at the height of the bed at any point is at a distance z from the datum. Okay. The water depth is given by y, a specific energy E is given here, all right, and the energy line is given dotted like this, and this is the water surface. Okay. So, first I will remove this, all right. So, the total energy H of a gradually varied flow can be expressed as, so now there is a little change from the equation that we have seen. In the uniform flow we have seen that it was H is equal to Z plus Y plus V square by 2G. Here a parameter is introduced, alpha. Okay. It is a parameter depending upon different conditions. If we assume alpha is equal to 1, that we have already assumed previously, all right. So, when we wrote the equation of the total head H in any in any type of flow, we got Z plus Y plus V square by 2G. So, that was actually under the assumption that alpha is equal to 1. In principle, we must have this equation. Z plus Y plus alpha V square by 2G. Okay. All right. So, if we assume alpha is equal to 1, we get this equation as first. Okay. H is equal to Z plus Y plus V square by 2G. So, the velocity head plus the pressure head plus the potential head. So, now if we differentiate both sides of the equation with respect to x, if we do that, we are proceeding in the same way as we did in the beginning. So, dH by dx will be dz by dx plus dy by dx plus d dx of v square by 2g, that we call equation number 1. So, now this actually represents the energy slope, that is dH by dx is equal to minus SF, all right. And this dz by dx represent the bottom slope minus S naught, all right. This dy by dx represent the water surface slope with respect to the channel bed, all right. So, the three terms dH dx represents the energy slope, dz dx represents the bottom slope, and the dy by dx represents the water surface slope with respect to the channel bed. Now, if you see, I mean for your convenience I am just keeping this figure here all the time. So, you can actually follow. If something comes I will just point it out. So, further V square, we say d, I mean just going into the sub part of that equation for d dx of V square by 2g. So, V square by 2g can also be written as V square by 2g can also be written as V is q by a, okay, all right. So, it becomes q square by 2g a square, and this is what has been put here, all right. This you should be clear. Now, what we do, what we say is, so instead of writing d dx of V square by 2g, so let us say this is a, for example, capital A. So, what we write is d dy of a into dy by dx. This is the simple differentiation rule that you already know. Okay. So, dA by dy can be written as dA so dA by dx can be written as dA by dy into dy by dx. So, same principle we have used here, all right. Or we simply write d dx of v square, left hand side remains the same. Now, looking at the right hand side, what we say is, so q square is constant, 2g is constant, so it comes out, but we differentiate a with respect to the y. So, it becomes, so let us differentiate this, I mean let us see this part. So, it will become q square by 2g will be there, and when 1 by a square will be differentiated, it will become minus 2 by a cube, okay, into dA by dy, this particular part, okay. And then, so this is what exactly is written, 2 and 2 gets cancelled, this becomes q square by ga cube. You see, q square divided by ga cube into dA by dy, and this dy by dx comes as it is, all right. So, this dA by dy, rate of change of area with respect to the depth, is called T, where T is the top width of the channel, okay. So, we are trying to obtain an equation in a slightly different form than what we have seen before, all right. So, here T is the top width of the channel. So, this equation can be rewritten as, so if we rewrite equation 1, the dH by dx was minus Sf, dz by dx was minus S naught, this dy by dx is the same, and this becomes q square T by Ga cube from the previous slide, all right, and this dy by dx. Each term you have understood now. So, we rearrange and we take this S naught on this side, and dy by dx we take common. So, let me do it for you here and then you will follow. So, dy by dx, so basically so I am taking S naught this side. So, this becomes, and Sf will be the same, is equal to dy by dx common 1 minus q square T by Ga cube, all right. So, dy by dx is going to be S naught minus Sf divided by 1 q square T by Ga cube. This is exactly same as this, all right. So, it is written in a more, you know, so just directly we have written, but now we have shown also. So, this equation is a differential equation of gradually varied flow. We have actually obtained the same equation, just that we did not have T and it was not in form of T and A. If you remember, I can, you know, take you to that particular slide. So, okay. So, I will show you where we had done that. See, we have obtained the similar equation here, you remember, but this one. So, it is of a same form, just that we will later see in the gradually varied flow, this is actually Froude number whole square, all right. The way of derivation was different. So, okay, we go back. We were here. So, actually this value q square T T by Ga cube is Froude number whole square, where Fr is the Froude number. All right. So, you can try Froude number whole square is equal to V square by Gy. All right. So, it will be Q square by A square into Gy. All right. So, if you multiply A this one, okay. So, it will be Q square A divided by A cube G into A into Y. So, A by Y is can be written as T, top width. So, Froude number whole square is Q square T by G A cube, because Froude number is V by under root G Y. All right. So, you have also seen that y g q square T into G A cube is Froude number whole square. All right. So, this equation is the same as we obtained. We obtained was S naught minus S f 1 minus same. All right. So, now the classification of flow profiles. What are the flow profiles in gradually varied flow? So, if the flow rate Q, Manning's number n and S naught are fixed, okay, then the normal depth y naught and the critical depth y c is also fixed. All right. You understand this? See, Q is equal to 1 by n is the Manning's equation is V by n S to the power half R h to the power 2 by 3. All right. So, S naught is fixed, n is fixed, V is there, then Q, depending upon the cross section, Q by A, that is also going to be, fixed. So, this normal depth y naught and the critical depth y c is also fixed, if we know all these three values. So, this is the depth y naught is the depth which is obtained from the uniform flow equations. All right. So, there could be three possible relationships that may exist between the normal depth y naught and the critical depth y c. All right. One, that the normal depth can be greater than the critical depth. Second is that the normal depth is less than the critical depth, and the third one is that the normal depth is the same as the critical depth. Further, y naught does not exist when, there will be no y naught if the channel bed is horizontal, that means S naught is equal to 0. The channel, if it has an adverse slope, then also there will not be any normal depth, that means S naught is less than 0. And based on these, the channels, so based on these conditions, the channels are classified into 5 categories, the channels itself. One is mild slope, that is called M, where the normal depth y naught is greater than the critical depth. Okay. So, this implies that the flow is subcritical at normal depth. All right. See, Fr is equal to V under root G y naught. If y naught is greater than critical depth, then Froude number is going to be less than 1. So, if the normal depth is greater than the critical depth, that is subcritical flow at normal depth, then this is called mild slope. A steep slope is when y naught is less than y c. Y naught means normal depth is less than the critical depth. Here there will be supercritical flow at normal depth. How? F r is V by under root G y naught. If y naught is less than y c, that means the numerator is decreasing, denominator is decreasing, therefore, this will increase. So, this is going to be greater than 1. So, that is it is supercritical. At critical slope, this is called the critical slope C. So, mild slope is denoted by M, steep slope is denoted by S, and critical slope is denoted by C. Y naught is equal to Y C indicates that at normal depth there is a critical flow. All right. The horizontal bed means S naught is equal to 0. That is very simple to understand, right? Horizontal bed means S naught is equal to 0, and then in the adverse slope S naught is equal to 0. So, using all the conditions before, there could be 5 different type of channels. One is mild slope channel, steep slope and critical slope, and when the normal depth does not exist, in that case it is simply defined either as the horizontal bed, because there is going to be no normal depth in a horizontal bed, and also in the case of adverse slope when the slope is less than 0. So, in that case also there is not going to be any normal depth. So, it is just defined based on S naught itself, called horizontal bed and adverse slope. Okay. Mild slope, steep slope, critical slope, horizontal bed and adverse slope, M, S, C, H and A. So, this is important to remember. The mild is where y naught, that the normal depth is greater than the critical depth. Steep is when the normal depth is less than the critical depth. Horizontal bed is very clear, adverse slope is also very clear, all right, and critical depth is the easiest one to remember. So, this too, the horizontal bed and adverse slope cannot sustain uniform flow. So, the lines which represents a critical depth called CDL and the normal depth is called NDL. When drawn in longitudinal section, divide the flow space into following 3 regions. You are going to see. Region 1 is, so at the critical depth, if we draw that line in the longitudinal section at like this, then that line which represents the critical depth is called CDL, and the one that represents the normal depth is called NDL. So, for example, just I will draw this. For example, this is there, right, this is a channel, for example, I mean does not even necessarily. So, suppose this could be anything, right. So, this represents line 1, this is line 2. So, actually it is going to divide into 3 regions, right, region 1, region 2, region 3. So, that is what we are actually talking. We will show you the exact these NDL, HDL in upcoming slides, but just to tell you why there are several regions. So, region 1 is the space above the topmost line, very normal as I showed you. Region 2 is the space between the top line and the next lower line, correct, and region 3 is going to be the space between the second line and the bed or the lowermost region. So, these are the 3 regions depending upon where the CDL and NDL is. So, this is an example we have just, I mean this diagram number 1 indicates in case of a mild slope shows 2 regions. What was the criteria? The normal depth. So, this is normal depth, right, and this is critical depth. So, this is the line that shows NDL, corresponds to normal depth, CDL corresponds to critical depth. All right. So, this represents a mild slope. All right. So, as you see, this is region 1, this is region 2 and this is region 3. See here this figure represents a steep slope. Why? Because the critical length yc, critical depth yc is greater than y naught. So, CDL is above NDL. All right. The third region is critical slope. So, CDL and NDL are same. So, here there will not be any region 2. So, region between the CDL and NDL is called region 2. So, basically there is going to be two regions, region 1 and region 3. All right. The fourth is a horizontal bed. There will be no NDL here. So, there is only be a CDL because the bed is horizontal. All right. So, there is not going to be, there will be only region 2 and region 3. All right. Similarly, here in case of adverse slope also, there is not going to be existence of NDL, only CDL will be there. So, that existence of only region 2 and region 3. So, this figures have been adopted from Subramanya, Flow in Open Channels, this book. I think it is a very nice book for open channels, of course, very detailed, might not be fully, this is only 1/6 of the course, this open channel flow. So, I mean you can read these topics from there, that will give you a good idea. All right. So, there can be three, as we have already seen that the profiles, there is mild slope, there is steep slope, there is critical slope, there is horizontal bed and there is adverse slope. So, depending upon the three regions, there could be three different type of profiles. If y is greater than, so region 1 is called M1, region 2 is M2, region 3 is M3, same S1, S2, S3, C1 and C3, and this one is H2 and H3, and this adverse slope is A2 and A3. This is very clear, right, because if the y is located both above the normal depth and the critical depth M1, if it is located in between, it is M2. So, just by region wise, you see these regions here. And so on. Okay, here H2, H3, A2, A3, all right, and this is C1 and C3, C1 and C3, all right. So, mild slope, this is a figure showing mild slope, all right. We have already drawn this. Okay. The steep slope represents like this, you see the CDL, the NDL, you see S1, S2, S3, this is horizontal asymptote, all right. So, critical slope, so the horizontal asymptote C1 and C3, all right. So, I mean there is much more detail to it, but at undergraduate level only what what I am teaching is only required, the identification of the regions, what is mild slope, what is adverse slope, what is horizontal bed, all right. So, the horizontal bed is like this, this area is H2 and this area is H3, all right. So, if the profile is like this and if the profile is like this, it is H2. So, profile is like H2, this is H3. This is just to show you. Adverse slope looks something like this, which you already know. All right, if the water level is like this, it falls in A2. If this is in this one below CDL, it is A3. So, these all figures have been taken from Subramanya. So, I think this is a nice and appropriate point to stop. So, we will solve couple of problems in our next lecture for related to the gradually varied flow, and then we will continue to the other topic called the rapidly varied flow. So, thank you so much for listening. I will see you in the next lecture.